All right, guys, good afternoon, and thank you for attending this session. And my name is David Luo. I'm from Mythic Incorporation. Today, and my colleague, Dr. Zdeněk Přikryl here, and I will join to present this particular paper here. The title is How to use and extend the RISC-V in an analog matrix processor for the neural network. So a couple of quick introduction for both companies. I'm from Mythic, and Mythic is an AI startup company. Our goal is to enable the deployment of AI solution in the edge devices across different industries. Our key technology is using analog computing memory to perform the neural network inferencing. Codasip is a leading provider of RISC-V processor IPs and processor design automation tools for the designing and the customization IP cores. They are also one of the sponsors here. Mythic main product is a SoC solutions called Analog Matrix Processor, called AMP. And the matrix analog processor consists a two-dimension array of lots of computation tiles stitched together, just like the picture showed on the right-hand side. It's a two-dimension arrays, and with lots of identical processors stitching together through a on-chip network on-chip routers. And our SoC is able to support multiple concurrent neural network models, and all the weights has been put on chip, so you save lots of off-chip memory, as well as performance improvement. This little square on the right-hand side of the image is a Mythic tile. And Mythic computation tile has a couple of components. One is the analog compute engine called ACE. And also we have a processor, RISC-V processor in each tile, and a SIMD data engine, a scoreboard, and some SRAM, local SRAM to each individual tile. And as also mentioned, a network on-chip router connects everything together into a two-dimensional mesh fashion. And within each ASE, and it's our analog compute engine, and we store the neural network weights in a non-volatile flash memory, and that technique saves lots of data movement as well as external memory storage. And we also compute the matrix multiplication directly inside the flash memory arrays. And that's how the techniques we achieve the performance enhancement as well as a power saving by avoiding moving lots of data around. Now, a embedded RISC-V processor play a key role in our solution, ASE, analog compute engine. And the three main functions of each processors will do within the tile. And first one is manage the hardware scoreboard, and because we have a data dependency and as well as a resource dependency driven by the neural network data flows. So the RISC-V processor manages this particular dependency checkers. The second one is, because this is a data flow driven processing, each workload and especially associate a long word, a workload command. And the RISC-V processor will have to manage and format such a long workload commands. And also the last one is issuing this particular workload commands, and for the best of the highest throughput and the lowest latency whenever the triggering condition being met. Triggering condition meaning data set is available. Also, you have the hardware resources available for you to perform the calculations. Now, when we make the selections of embedded processor, and we definitely have a few choices, just like lots of people in the industries. And we consider three key criteria. One is flexibilities. Because our application thinks we have a dedicated data engine to calculate the informations, then our embedded processor is really runs a application-specific control loop to manage the hardware dependencies called a scoreboard, and also format the command and launch the instruction for the command workload command. So we would like to have a flexibility to add customized instructions and so that we can reduce the memory footprint as well as improve the performance. The second criteria is really we like to have a very low interrupt low latency interrupt. And because this is a data flow driven, and whenever data is coming available, and the processor have to respond very quickly. Of course, in the low power mode, and when it's idle, and when we don't have any data process, low power mode is a key. And the very last one, as you can, if you guys see the initial pictures, we have so many individual identical tiles and being integrated in our SoCs. So we want our embedded processors is cost effectively in the power, performance, and the area as we instantiate so many tens or hundreds in our SoCs. So with all these key criteria, when we select our choice of a processor, and the RISC-V from Codasip fits the bill and fits very nicely, meets all the criteria. So for now, I will hand over to my colleague, Zdeněk, to finish the remaining presentation. Page it out.
Okay, thanks. Before we dive into the details of the CPU itself and what we did, let me just briefly introduce our company and the way how we handle the customizations that we did in the end. So first of all, Codasip is a leading provider of RISC-V processor IPs. We have a wide selection of them, starting from the low power cores that I will talk about in a minute, up to the application class, the MP multiprocessor solutions, and kind of anything in between. All of them are configurable and customizable, and I will touch these two terms in a second because in the Codasip world, it means different things. As mentioned, we have also tools by which we customize or configure the cores. And the main idea behind that is that the CPU is described using high-level description language in which we capture the CPU, meaning architecture as well as microarchitecture. And then you just press a button and you obtain the compiler, low-level programming tools, simulators, RTL, verification tools, pretty much anything that you need for such a CPU. So I mentioned we have a wide selection of the CPUs, but for this project, we went with the L30, which is our small NAF efficient core. It's a three-stage design. And if you look at the block diagram, then it's something that you would expect. So you have these low-level latency interrupt controller, you have the WFY for power modes, you have a debug module. Then you have a selection in the case of the ISA, so there's a few pre-configured like EMC, IMC, but you can play with this one even more, and you can, for instance, disable the M mode, or you can disable the C extensions, so this is really up to you. It's also quite configurable on the memory subsystem side because you have PMPs, you may have the TCMs, caches, you may also, have only iCache if you need that. So it's quite configurable. But more importantly, the blue box that you can see there, it's a user custom extensions. So what that means? Well, it means that you can play with the ISA. You may add instructions there, and you can also change things like pipeline if you need that, or you may add a coprocessor interface or any interface that you want in the end. So it's not just about the instructions that the point is. It's also, you can also configure things outside of the ISA. Now going back to the configurable/customizable, what that means? Well, by configuration, we mean that we select something that is already pre-verified by us, and a customer can just select from this kind of menu what we already have. And in the case of customization, it means that you go beyond that. So you do things like acceleration through the interface or accelerator interface. You do things like new instructions and things like that. So how these are done? Well, it's done in a way that, as I mentioned, is described using this high-level description language in which we capture the architecture as well as microarchitecture. It scales well from the embedded up to the application class because every single IP that we have, and that includes the MP, is described using this architecture language. And then if you have this description, then you can click on the button and you get all sorts of the outputs. You get the SDK that consists of the C compiler that's aware of every single instruction that you have inside of your design. And the compiler is smart enough to use these instructions automatically without using or going to the intrinsics world or inline assembly world, unless you want to. So the option is still there, but you don't have to do that if you don't want to. Then you have a couple of other things inside of the SDK, such as simulator, profiler, debugger, all sorts of things that you need for software development. Then you have the RTL. It can be Verilog, System Verilog, or VHDL. Besides that, you have the some test benches, some EDA scripts for the RTL simulators and so on. So pretty much anything that you need for the CPU integration. And last but not least is that you get also verification tools out of the description. And by verification tools, I mean UVM test bench, for instance, that tuned according to the architecture that you designed. So for instance, if you change the API of the CPU by adding a processor interface, the UVM test bench is aware of this one and allows you to just play with that. There are a couple of other tools like random program generator and so on that really helps during the verification phase, because we are, by the way, huge believers in verification, that it is an important part of the CPU design. If you look at the arrow that goes back to Codel, the point is that if you do some changes, such as adding instructions, or if you find some problem on the verification side, all you need to do is just go back to Codel, change the Codel layer, click on the button, and you have the fresh outputs out of that. So we had a nice demo today, so I'm not sure who attended, but it's, what we tried to show there is exactly this loop, because this loop can be quite powerful. Now going back to what we actually did to L30. Well, we started and we configured that as a RV32 IC. So as you can see, there's no multiplication or division, it's not needed. It's iCache only, so the Dcache is disabled in this case, but we added the wide low store interface, which is able to feed the data efficiently in. It has on-chip debugger, and of course it has a low latency interrupts and power WFI features in there as well. So this is the layer that customer can choose from, because this is something that we already pre-verified, prepare, nothing really complicated. And then what we did on top of that is that we've added coprocessor interface that the Mythic needed in their architecture, and so this is the kind of microarchitecture tweak. And then on the architecture side, we added some ISA extension. So roughly it's about 70 instructions, and where the domain is different. Let's say the areas of the instructions targets the DSP operations or the bit manip operations that are on top of standard bit manipulation operations. Some advanced DSP instructions such as zero overhead loops. And of course, because we have a coprocessor interface, we have to have a way how we can control that. So there are instructions that work with that one. So if you look at the nature of instructions, some of them are used automatically by a compiler, such as bitmanip or DSP. Some of them are used through the intrinsics, such as coprocessor interface, because there is no way our compiler can know how to control operations outside of the core itself, which is in this case coprocessor. The last thing that I'd like to mention here on this slide is that from the spec to the deliveries, it was less than 2 months in a small team. So really, optimal or productive way how to do this customization work. So the last one, I'll conclude this presentation. I think that everybody knows there that the RISC-V really targets a wide range of the applications because it's nature of RISC-V. It encourages people to do customization and innovation through the custom instructions because it's well prepared for this one. So this is the reason why RISC-V is important here. Then, in the case of a Mythic, they created a nice use case for such RISC-V core using their analog matrix processor that combines the analog part, the digital part using our core plus SIMD on-chip memories and so on. And this was a natural kind of blend, because we do have something that the Mythic could start from. We just added the additional layer, innovate a bit, and then we have a final solution in a fraction of the time. That's all.